See, we discussed Geiger-Marsden experiment, Rutherford's atomic model. Okay. Bohr also studied this atomic model suggested by Rutherford. Rutherford's atomic model is known as planetary atomic model. He suggested this thing just like the planets revolve around the sun. Electrons in the atom revolve around nucleus. But here, when scientists obtained the atomic spectra for hydrogen, we already discussed different series, Lyman series, Balmer series, Bastian, bracket, Fun series. So these spectra obtained are line spectra, right? But if we consider Rutherford's atomic model, then what happens if electron is revolving around the nucleus? Means its motion, that is accelerated one. And classical electrodynamics says this thing: when any charged particle is executing the accelerated motion, then it emits the energy in the form of radiations. So if electron is continuously emitting the energy, then its energy will be continuously decreasing one. And if its energy is continuously decreasing one, then the radius of the orbit for its revolution is also continuously decreasing one. And if this process continue, then the motion of the electron, that will be spiral one. And finally, after some time, it will be at rest in the nucleus. So here the stability of the atom can't be explained, as well as if this one is true, then the emission of the energy in the form of radiations, that is continuous one. So the spectra, atomic spectra obtained, that should be continuous one. Okay. But here we are getting line spectra. So Rutherford's atomic model fails to explain this particular thing. So Bohr suggested the atomic model in terms of postulates. Clear to all of you? Bohr suggested the atomic model in terms of postulates. And in these postulates, he combined classical and quantum mechanics. So first postulate he suggested like this: electrons can revolve in such orbits which are known as stable orbits, in which they will not emit the energy or they will not emit the radiations. And these orbits in which electron revolves, which are known as stable orbits, in those orbits, the angular momentum of electrons, that is always in the integer multiple of h upon 2 pi. So angular momentum of electrons in these orbits, which are known as stable orbits, that is nh upon 2 pi, where n, that is 1, 2, 3 and so on. So this one was new concept. See, in chapter 11 we studied about the quantization of energy, energy quanta. This one is the concept of quantization of angular momentum. Okay. Then third postulate he suggested like this: when electron is transited from higher energy state to lower energy state, means higher orbit in which it possesses more energy to the lower orbit in which it possesses less energy. So the transition when higher to lower takes place, at that time the energy is emitted in the form of radiation. And this energy emitted, that will be exactly equal to the difference of the energies in those two orbits. It implies that if electron is transited from ith orbit to jth orbit, where ith orbit is greater than jth one. Now, in ith orbit, if energy of electron is Ei and in jth orbit, energy of electron is Ej, then when the transition from ith to jth takes place, the energy emitted in the form of radiation, that is Ei minus Ej, and that will be equal to HF, where F, that is the frequency of that emitted radiation. Clear? Or we can write that energy equal to Hc upon lambda. Clear? So, in this way, Bohr suggested the atomic model. Clear to all of you? Now, if we apply this Bohr's model to hydrogenic atom, then we have the equation for orbital speed, that is 1 upon 4 pi epsilon 0 e square upon mr raised to 1 by 2. This equation we already derived previously. And equation for the orbital radius, that is e square upon 4 pi epsilon 0 mv square. Now, angular momentum is given by mvr for the electron revolving around the nucleus in orbit. So if electron is in nth orbit, then we can write here the angular momentum in nth orbit, that is equal to m orbital speed in nth orbit and radius of nth orbit, and that is equal to nh upon 2 pi as per Bohr's second postulate. Okay, so we can write here now, as per this equation, Vn square equal to 1 upon 4 pi epsilon 0 e square upon m, and this r is Rn, because this one is in nth orbit that we considered. So we can write Vn, that is equal to 1 upon 4 pi epsilon 0 e square upon m Vn Rn. From this Vn square, one Vn is taken on right hand side. Okay. Now this denominator m Vn Rn, that is angular momentum, but angular momentum is nh upon 2 pi. So we can write Vn, that is equal to 1 upon 4 pi epsilon 0 e square upon nh upon 2 pi. Resultantly, we will get Vn, that is equal to e square upon 2 epsilon 0 n h. Okay. Now here, if we multiply and divide by 2 pi, then we can write here 1 upon 4 pi epsilon 0, that is constant k. So another form that we can write 2 pi k e square upon nh. And here we can observe this thing, the orbital speed Vn proportional to 1 upon m, because see, all these are constants. Okay. So Vn proportional to 1 upon n. This is the equation of orbital speed. Clear to all of you? Now, orbital radius for nth orbit. So as per this equation, we can write that is Rn equal to e square upon 4 pi epsilon 0 m into 1 upon Vn square. So that is equal to e square upon 4 pi epsilon 0 m. Now substitute the equation of Vn, right? And that is this equation. So Vn square e raised to 4 upon 4 epsilon 0 square n square h square. So that denominator to denominator is written here in numerator. Now 1 epsilon 0 cancel, 4 cancel, 1 e square will cancel. Finally, you will get the radius of nth orbit, that is n square epsilon 0 h square upon pi m e square. So here Rn proportional to n square. Suppose we take n equal to 1. N equal to 1, that is called ground state. So R1, that is also known as Bohr magneton. So that is denoted by A0. Substitute the values of epsilon 0, h, pi, m and e. You will get the answer 5.29 into 10 raised to minus 11 meter. Now, if we remember this one, then radius of the second orbit, that is n equal to 2. So 4 into this one. For third orbit, 9 into this one, like that. So we can calculate the radius of nth orbit by this particular equation. Clear to all of you? Now see, we derived the equation for radius of the nth orbit, Rn equal to n square s square epsilon 0 upon pi m e square. Now we have the equation of the energy, that is E equal to minus 1 upon 8 pi epsilon 0 E square by R. So for nth orbit, we can write En equal to minus 1 upon 8 pi epsilon 0 E square upon Rn. So En equal to minus 1 upon 8 pi epsilon 0 E square upon, substitute this particular value of Rn here, n square s square epsilon 0 pi m e square. Okay, pi cancelled, take this m e square in numerator. So En equal to minus m e 4 upon 8 epsilon 0 square n square h square. Now see here, we can rewrite this one like this. En equal to minus me4 upon 8 epsilon 0 square h square into 1 upon n square. Means see this part, this bracketed term, that is constant one. So we can say energy in nth orbit that proportional to 1 upon n square. Now here suppose we substitute the values of m, e, epsilon 0 and h. And if we solve it, then we will get 2.18 into 10 raised to minus 18 upon n square joule. Now to convert this one in electron volt, divide this one by 1.6 into 10 raised to minus 19. So now we have energy in nth orbit minus 2.18 into 10 raised to minus 18 upon n square into 1.6 into 10 raised to minus 19. Now if we solve this one, we will get energy in nth orbit, that is minus 13.6 upon n square electron volt. Now see here, in this particular equation, suppose we substitute n equal to 1. So n equal to 1, that is ground state. So E1, that is equal to minus 13.6 upon 1 square, that is minus 13.6 electron volt. So this one is the energy of electron in ground state. We already discussed this thing. This negative sign appears here. Means when total energy comes to negative, then that is binding energy. Means if electron is revolving in ground state, means it is bounded by this much energy. So if you want to make that particular electron free, then we have to make its energy equal to 0. So we have to supply the energy equal to 13.6. So minus 13.6 plus 13.6, that will come to 0 and electron will be free. Now if we substitute n equal to 2, then E2, that is minus 13.6 upon 2 square, that is minus 3.4 electron volt. So this is the energy in second orbit. And this one is known as first excited state. Similarly, when you take n equal to 3, then it is called second excited state. When you take n equal to 4, it is called third excited state. એટલે અહીંયા ખાસ ધ્યાન રાખજો. MCQ1 એક્ઝામ્પલની અંદર ઘણી વખત એ લોકો લખે કે સેકન્ડ એક્સાઇટેડ સ્ટેટ, થર્ડ એક્સાઇટેડ સ્ટેટ. તો ખ્યાલ રાખવાનું કે n વેલ્યુ શું લેવાની છે તમારે, નહીંતર ગડબડ થઈ જશે. ઓકે. So in this way, we can calculate the energies of electron in different orbits or different states. Clear to all of you? Now in third postulate, Bohr suggested this thing when the transition of electron takes place from higher orbit to lower orbit or higher energy state to lower energy state. At that time, the energy is emitted in the form of radiation, and that is equal to the energy difference between those two levels. Okay. So now let's check this thing. Okay. Now see, we already derived the equation for energy in nth orbit, that is En equal to minus me4 upon 8 epsilon 0 square h square into 1 upon n square. Suppose electron is transited from ith orbit to jth orbit. So in ith orbit, we can write the energy EI, that is equal to minus me4 upon 8 epsilon 0 square s square into 1 upon ni square. Clear? And in jth orbit, EJ, that is minus me4 upon 8 epsilon 0 square s square into 1 upon nj square. So when the transition from ith to jth will take place, the difference of these two, that much energy will be emitted in the form of radiation. So this minus this. Clear? Now, if the frequency of the emitted radiation, that is F in suffix ij, represent the transition, that is from I to j. So this energy difference, that is HFIJ, that is equal to, now here we can take me4 upon 8 epsilon 0 square s square common, this minus minus plus, so 1 upon nj square minus 1 upon ni square. Now we can write F, that is C by lambda. So Hc upon lambda ij, this is the wavelength of the emitted radiation, that is equal to me4 upon 8 epsilon 0 square s square into 1 upon nj square minus 1 upon ni square. Now take this Hc on right hand side. So we will get 1 upon lambda ij, that is equal to me4 upon 8 epsilon 0 square h cube c into 1 upon nj square minus 1 upon ni square. Now see, this equation obtained have the form exactly like the form of the equation for the wavelengths obtained in different spectral series. That is 1 upon lambda equal to r, the Rydberg constant, into 1 upon m square minus 1 upon n square, where m and n are integer numbers. Okay. So here these are the number of orbits. And here very important thing, that is this one. This constant me4 upon 8 epsilon 0 square h cube c, if you calculate the value of this one, then it comes to 1.09 into 10 raised to minus 7 meter inverse, and that is exactly equal to Rydberg constant. It implies that this one is in perfect analogy, sorry, 1.09 into 10 raised to 7 meter inverse. This one is in perfect analogy with the experimental observations. Clear to all of you? Now let's check the frequencies or wavelengths obtained in the experimental observations in line spectra can be justified with the help of these theoretical obtained equations or not. Okay. Now see here. Suppose first we think about Balmer series. So equation for the wavelength in Balmer series, that is 1 upon lambda equal to r into 1 upon 2 square minus 1 upon n square. Clear? So base orbit, that is second one, and n value, suppose we take 3, 4, 5. It implies that if the transition of the electron takes place from 3 to 2, 4 to 2, so when the transition takes place from 3 to 2, then we get the H alpha line of Balmer series, that is with wavelength 6563 angstrom. Now see here. This one is the energy in second orbit, E2, that is minus 3.4 electron volt. And this is the energy E3, minus 1.5 in third orbit. Now suppose the transition takes place from 3 to 2. So now that is the H alpha line of Balmer series. Clear? Now what is the difference between these two here? So minus 1.51 minus 3.4. So here the energy difference, that is 1.9 electron volt. So here the radiation emitted, that is with energy equal to 1.9 electron volt. And if the frequency of this emitted radiation is F, then we can write this energy 1.9 electron volt, that is HF, but F equal to C by lambda. So we can write that is equal to HC by lambda. So lambda, that is HC by E, H 6.625 into 10 raised to minus 34, C3 into 10 raised to 8, energy in electron volt. So in joule we can write 1.9 into 1.6 into 10 raised to minus 19. And if you solve this one, then you will get the lambda, that is a 3.7 nanometer. Clear? That is very close to H alpha. Clear? So in this way one can explain that particular atomic spectra obtained for hydrogen atom. Clear? Now see in the text on page 427, the energy level diagram that is given to you, and that is nothing but the graphical presentation of energies in different state. So minus 13.6 electron volt, that is in ground state, that is for n equal to 1. એટલે આપણે અહીંયા આગળ જે કેલ્ક્યુલેટ કરીને આ લખ્યું છે એ લાઈન ગ્રાફના ફોર્મની અંદર ટેક્સ્ટમાં ખાલી બતાવેલું છે, રાઈટ? એન્ડ એઝ વી મૂવ ઇન અપવર્ડ ડાયરેક્શન, એટલે કે આઉટર ઓર્બિટમાં તમે જતા જાઓ એમ એનર્જી ઓફ ઇલેક્ટ્રોન વધતી જાય, કારણ કે જો નેગેટિવ વેલ્યુ ઓછી થતી જાય છે એટલે વધતી ગઈ કહેવાય એનર્જી. હા, ક્લિયર? અને difference between energies સક્સેસિવ ઓર્બિટ્સ માટે ડિક્રીઝ થતો જાય છે. એટલે જેમ જેમ ઉપર જતા જાઓ એમ એટલે કે ન્યુક્લિયસથી તમે જેમ દૂર જતા જાઓ એમ એનર્જી લેવલ્સ ક્લોઝ થતા જાય. ક્લિયર? તો એ આખો એનર્જી લેવલ ડાયાગ્રામ આપણને આપ્યો છે. ચલો એમાં કોઈને કઈ ડાઉટ ખરો બેટા? ક્લિયર છે? Now see here we calculated the wavelength of the emitted radiation during the transition of electron from n equal to 3 to n equal to 2. 2 that is the base orbit for Balmer series. Okay. Now see in the text figure number 12.9. So in that now you can understand when the transition of electron takes place from n equal to 3 to n equal to 2, you will get H alpha line for Balmer series. Then if the transition takes place from n equal to 4 to n equal to 2, then you will get H beta line of Balmer series. Then n equal to 5 to n equal to 2, then you will get H gamma line of Balmer series. So in this way, when the transitions takes place from 3, 4, 5, 6, 7 orbits to second orbit, then we will get entire Balmer series, and we can calculate all the wavelengths as per this particular calculation by taking the difference of energy levels. Then after, if the transitions takes place from second, third, fourth, fifth orbit to ground state, means n equal to 1, we get entire Lyman series. Okay. Then after, if the transition takes place from 4, 5, 6, 7 orbit to third one, clear? Then we will get the Paschen series. In this way, all the series is obtained experimentally that can be calculated here with the help of this particular method of the energy difference between two energy levels of the transitions. Clear to all of you?